More interest today. Very interesting. Or not. Kind of not interesting. Let's see, I feel like I'm forgetting something. Next homework assignment is due Friday, homework G/H. So, of course, you're welcome to turn it in up to the 24 hours later on Saturday. So, just so everyone's aware, like in case I hadn't made it clear already, homework is due on a certain day on Gradescope, and then you can always turn it in up to a day late because, like, I know not everyone gets everything done on time all the time. So, if things are going later than that, you need to come talk to me. So that generally, I would like people to do the homework. I understand not everything gets done all the time. I also do drop, I think, the 3 lowest homework assignments is what I think I've written on Canvas. Certainly what I intend to do, even if I haven't written on Canvas. So in case that wasn't clear, that is something that is true. So if you missed one, not going to be the end of the world. Also for quizzes, I dropped the lowest quiz. So it's like, not going to be terrible if you miss some stuff. But the point is to do it all so that you can learn the stuff, right? Because really, I mean, I can talk here a lot, obviously I do, and say a lot of words about math, and you can hear them and probably get a little bit of something from that. But really, the way most people, I think, actually learn the math is by doing it with the homework and other problems. So, I mean, you should come to class. I'm not saying don't come to class. You should definitely come to class and listen to me say things and ask questions if there's an opportunity to. But really, doing the homework is how you're going to actually learn some stuff. So make sure you do the homework. Yeah. Questions before we get started? Here's the fun fact. Throw that the math. My middle name is spelled terribly. Jeffrey. My middle name. My parents wanted me to be like Joffrey, like with a G, because my dad's friend's name was Joffrey with a G, but they liked the J letter for my middle name better, so they wanted me JJ Parmenter, so they spelled it Jeffrey, J-E-O-F-F-E-R-Y. Fun fact. All right, so let's talk about compound interest, which we already really kind of talked about last class. Compound interest is just basically the idea that after your money earns some interest, then you start earning interest on that. The idea with compound interest is that you don't just compound it every year. You can compound things more frequently than once every year. So let's see, is there anything I'm missing? Interest is, yeah, so let me read the official words here. Interest is added to the principal regularly at intervals more often than once per year. So the added interest may also earn interest from then on. So really, this formula here for compound interest encapsulates the formula from last class. Right, if you let n equal 1, where n is the number of times you're compounding per year, this formula here is exactly the same as, or do I still have it from last class? Maybe I do. If I'm smart, yeah, I do. If I keep old stuff on you. Yeah, so just so everyone can see this for a second here, right? If you take this formula and you let n equal 1, you're exactly getting this formula up here. A equals P times 1 plus R to the T. So really, this formula takes that formula with it along the way. All right. So, but you don't have to only compound once per year. You can compound things twice per year, which we would say was semi-annually, or 4 times per year, which would be quarterly, or once every month, which would be monthly, which would be 12 times per year, or once every day, or once every week, right? There's lots of different things, and we have to kind of know how many of those things are in a year. So if I said weekly, we'd be doing it 52 times per year, even though there's not exactly 52 weeks in a year, we just kind of go with 52. We said daily, we'd assume 365. We're not going to be like, oh, it's a leap year, there's 366. So we're just going to say the number of times being whatever. You could also compound interest every minute, which would be 525,600 times per year. If you've ever watched Rent, you would know that's how many minutes are in a year. If you haven't watched Rent, I mean, you're not missing out that much. It's a decent musical, but it's not like the best ever. Anyway, so speaking of musicals, sorry, I found us musical movies. I found us some really great news the other day. There's going to be a sequel to the Enchanted movie, which I'm very excited about. So it's called Disenchanted. Anyway, back to math. All right, so let's actually write down what things mean here. So A, and these things are the same as last time with one additional piece. A is the amount of money after t years. P is once again the principal, also known as the amount of money that's being invested or borrowed, the amount of money that someone's investing. R, again, is the interest rate as a decimal. N, well, actually, let's write T here. T is the number of years. And finally, the new thing that makes this formula a little bit different is N, which shows up twice. N is the number of times we are compounding per year. And then I'm going to make one brief sort of observation about this before we move on, because we're going to use it a little bit later today. I could use my exponent rules to rewrite this in a slightly different way. I could rewrite this as A equal to P times brackets, parentheses, 1 plus R over N to the N to the T power. So I want everybody to see that's really the same, because if you have a power to a power, what could you do with the powers? So what was that? So if we have a power to a power, we get to add or multiply the powers. Add or multiply. Add or multiply. Good question. So just so everyone's on the same page, just real quick. Right, when we have a power to a power, like 2 to the 3 to the 4th, that's going to be 2 to the 3 times 4. So we multiply them. Whereas if you have something like 2 to the 3rd times 2 to the 4th, that's where you add the powers. It is loud out there. I'm going to close that door. Hey, man, it's about to not be loud. It's really have to close the door. So here, these are totally the same, because we could multiply the nth power times the t power and get n times t. So those are totally the same thing. We're just going to use this version of it at one point later on. So I wanted everyone to be like, oh yeah, these are the same. Just like last time, most of the things we ask about compound interest are kind of just finding all the right values, throwing them into a formula, and then kind of using the calculator. Question? Sure. Yes. Number of times we compound per year. So if we were compounding 4 times, if we were compounding it quarterly, n would be 4, because n would be the number of times we compounded per year. So let's look at some examples. Keep things in order here. So let's see what we've got here. We have $1,000 to invest. We plan on investing it for 10 years. And you have 2 choices for account. One that pays 6% simple annual interest, or the other one paying 6% interest compounded monthly. Which one would you choose? The objective being, of course, to get the most money, right? I mean, you're investing money. The idea is you're trying to make money. So we're going to calculate both of them. Let's do the simple interest one first. So for simple interest, we're really just throwing everything into the formula. So we know that our formula is A equals P times 1 plus R to the tth power. And we're just going to sub in all the values we have. So our principal is $1,000 times 1 plus our value R is 6%, which is the decimal, is 0.06, or if you prefer 0.06, either way. And our T value is 10. So calculating this, if I plug this into the calculator, I would get, well, I'm going to do 1,000 times 1.06 to the 10th power. And that's going to be approximately 1,000 times. If I do 1.06 to the 10th power, I get approximately 1.79085. So that's going to be approximately $1,790.85. And really, it is just a plug into the calculator. Like, there's no other good way to kind of deal with that. I don't recommend the phone calculator, because it's usually, it has I wouldn't say it's problematic. It just is not as nice as like something else you're maybe more used to using. But if you want to calculate using your phone calculator, you would do 1.06, and then you would do x to the y, and then you throw in a 10 there, and oh yeah, you're getting 1.7908. So that's how you do that. I definitely recommend, like, I like a Texas Instruments calculator, like a TI-30 or a TI-80 or whatever, but the phone calculator will serve your interests as long as you are careful. All right, let's look at the other calculation. We want to know which one's going to be more. So let's compound it monthly. So for compounding monthly, what's our value of n? Right, n is definitely going to equal 12. The number of times we are compounding per year. So the formula is similar, not quite the same. The formula here is going to be 1,000. It's still the same principle. But now look how things change. I'm going to have 1 plus r divided by n. So it's going to be 0.06 divided by 12. And then my power is going to be to the n times t power. So it looks a little different. We're still going to calculate it in a similar way. So I would still use a calculator here. 0.06 divided by 12, that's going to be 0.005. So I've got 1,000 times 1 plus 0.005, and 12 times 10 is 120. If I was trying to simplify this as much as possible before I put it into a calculator, I would definitely rewrite it as 1,000 times 1.005 to the 120. And that's about all I can do without a calculator, right? I can't multiply the 1,000 through yet because I have to do the power first. And I definitely can't do that power in my head. No one should be, right? No one, and there's probably weird people that can be like, oh yeah, but not us, not me for sure. So let's see if we do that. I gotta go sideways here. Can I go sideways? Yeah, okay. So 1.005 raised to the 120th power, you get 1.81939. Okay, so that's approximately 1,000 times 1.81939. And then multiplying the 1,000 through, I'm just moving the decimal over 3 places and getting approximately $1,819.39. I guess I maybe should have rounded up to 40 cents because it was 0.39 cents, but I'm not too worried about that. So, which one's better? Compounding monthly or compounding once every year? Monthly. And the general thought or thing that we're going to see is that typically the more often you compound interest, the more money is earned, because you're essentially saying, instead of saying at the end of the year you get 6% of the interest, what this compounding really does is saying every month you get a 12th of that 6%. So every month I'm getting 0.5%, right? 0.005 is 0.5%, because 1% is 0.01, that's 0.005. So every month you're getting 0.5% of the interest. So like after 1 month, I would get $5, right? 5% of 1,000 is $50. 0.5% of 1,000 is $5. So after 1 month, I get $5. So now I have $1,005. And the next month, I'm going to get 0.5% of interest on all of that. So I'm going to get $5 and a little bit more. And then, right, each month I'm going to add on a $5 and a little bit more and keep getting more and more. So I'm compounding the interest on the increments I'm getting each month. So that's, let me say that again, just so I can be super, hopefully more clear about this. The idea with compounding monthly is every month you're getting a fraction of the interest you would have gotten at the end of the year, right? Instead of getting all 6%, which would be $60 at the end of the year, you're getting $5 the first month, and then $5 the next month plus a little bit more because you're getting 0.5% of that first $5 and so on and so on and so on. Okay, now you guys the. Now, the thing is, although it's certainly good to think about that, it's not necessary to be able to calculate. To be able to calculate this compound interest thing, we're really just saying, okay, here's a formula, toss all the numbers in the formula. So our job really is to just identify what's what. So in this next example, suppose we invest $5,000. So if I'm reading this question, I'm going to immediately say, okay, my principal is $5,000. Right? I like to kind of write down the information as I read the question. The savings account that pays 4% interest. Okay, so my interest rate is 0.04. Compounded weekly. My N is going to be 52 because there are 52 weeks in a year. How long will it take for your money to double? So this is actually a good kind of idea here. There's something else we should write down with this information. We're asking how long it takes until the amount of money we have is how much? Double. And what we start with? Right. Well, we start with 5,000. So if we double that, that's going to be. So we know that we're going to also end up setting the amount of money after however much time it takes equal to $10,000. Typically, with these sorts of problems, you will know all of the pieces in the equation except for one. And the thing that we don't know is the thing we're being asked to find. So in this problem, they're asking how long, aka how much time is it going to take until we have $10,000? Question. So there are 52 weeks in a year, right? So that's coming from the fact that we are compounding it every week. Right there. That means N is going to equal 52. So it's just whatever the frequency that we are compounding is just N is going to be the number of those things in a year. So someone said we're compounding daily. What would our N be? Right, because there's 365 of those things in a year. If someone said hourly, it'd be like 365 times 24, whatever that is. But that seems kind of silly. So let's throw it all into our formula. It's maybe a good idea to write down the formula again. So it's P times 1 plus R over N to the N times T power. Okay. So then I'm plugging in everything I have here. So I've got 10,000 on the left equals 5,000 on the right times 1 plus 0.04 divided by 52 to the N times T. So that's going to be 52 times, I don't know what T is, so I'm just going to write T power. And our job is to solve for T. So when we solve an equation like this, where you have a T or a variable in the exponent, we're probably going to have to use what kind of thing? A logarithm. Typically, when your variable is in the power, you typically have to use a logarithm to get it out of the power. Before we can do that, we need to get rid of this coefficient because this isn't being raised to the 52t power. So we're going to divide both sides by 10,000. Not by 10,000, by how much? By 5,000. And 5,000 divided by 5,000 is 1. And 10,000 divided by 5,000 is 2. So I've got 2 equal to 1 plus 0.04 divided by 52. Doesn't really simplify very nicely. I'm just going to leave it like it is to the 52t power. And now we're going to take the log of both sides. And even though I happen to be a fan of the natural log, it is typical when we are doing these sorts of compound interest problems to use log base 10. There's no good reason other than it's just kind of standard practice. You can use whatever log you want. I like natural log. You might like log base 10. Someone might like log base 3. I'm going to pick log base 10. So take log base 10. I didn't write it because we don't write it for log base 10 of 2 equal to log of 1 plus 0.04 over 52 to the 52t power. And the whole point of doing this was then we can bring this 52t power down in front of the logarithm. Use the power rule for logs. So now you can say that the log of 2 is equal to 52 times t times log of 1 plus 0.04 over 52. It's kind of gross looking, but we're almost done. I want to get t by itself, so I'm going to divide by everything else. I'm going to divide both sides by 52. I'm going to divide both sides by log of 1 plus 0.04 over 52. Again, I know not kind of the best ever, but that's what we've got. So we're going to have t equal to log of 2 divided by 52 times log of gross stuff over there. log of 1 plus 0.04 over 52. And this is where a phone calculator is probably not your friend, because plugging this onto a phone calculator is really easy to kind of mess up the process. So I would definitely encourage a more typical calculator here. If I was doing this on a regular calculator, I would do 1 plus 0.04 over 52 first, then take the log of that, then multiply by 52, and then do log of 2 divided by my answer. That's how I would use a calculator to do that. This is going to end up being approximately, sure, let's do a couple things. We can do one thing here. This is log of 2 divided by 52 times log of 1 plus 0.04 over 52 is approximately 1.00077, lots of sevens. And that's going to be approximately 17.32. 17.32 what? Dollars? Years, right? Because we're asking about the time, and time, unless someone is saying something else, time should be measured in years when we're talking about calculating interest. So 17.32 years. Yeah. If you are looking for help about how you would do this, like enter this into a calculator, because sometimes the process can be kind of strange. Happy to talk about it in office hours. It's not too terrible. It just requires a little bit of being careful. All right. So both of these problems, although this one's kind of ugly, still just plugging in all the pieces you know to a given formula and then solving for the one thing we didn't know. Let's see, what do we got next here? Yeah, all right. That's my favorite part. So let's look at this next part, which is kind of cool, I think. So let's see what we've got here. Suppose I loaned you $1, some nice guy, for a year. And I charged you, okay, not that nice, 100% interest. So, right, maybe it's only $1. How much would you owe me at the end of the year? Well, if we just compound it like with simple interest, if I just charge you 100% interest, I loan you $1. At the end of the year, how much do you owe me? Just $1? You owe me the $1 I lent you plus another $1 for the interest. So how much do you actually owe me? $2. So that's how much you would end up owing if we just charged it, if we just compounded the interest one time per year. So let's look at our interest formula so we can see that things are really going to do what we think they are. So our compound interest formula would have a principal of $1, an interest rate of 100%, and 100% as a decimal is just 1.00 or just 1, and a time of 1 year. And what we're going to do is we're going to let the number of times we compound the interest increase. That's so we're going to leave n as unknown. So here's our formula. It's going to be 1 times 1 plus r over n to the nt, and plugging in an r value of 1 and an n value of, and a t value of 1, we're getting 1 plus 1 over n to the n, which looks really small. I feel like that type could have been bigger there. There's our formula. So this is going to be, right, we were starting with this, a equal to p times 1 plus r over n to the nt. And we plugged in all the things we knew and we got that. Let's be a little bit clear here. R is just 100% interest. Okay, so there's our formula. The only thing we don't know is the number of times we're compounding. So n, once again, n is the number of times we're going to compound it. And so here's where I'm going to be more explicit about what I was trying to say before about how like that example, the first example where we have like every month, I was saying you got 0.5% of interest. We're going to see that again here in not the first example, but the second example. So how much, we already answered this question. You already told me you're going to owe me $2. Well, let's actually calculate it to see that the formula gets what we know we should be getting. It's nice to know when you're doing stuff like this, like if you think you know what the answer is, and then see the formula matches that, it's kind of nice to confirm, oh yeah, we were thinking the right thing. So let's see if I plug in my values here. So if I compound it annually, n equals 1, and the amount of money is going to be 1 plus 1 over 1 to the 1. Not very exciting, but that's 2 to the first power, which is 2, which is what we said we should get. So cool. I'll take my $2. Sounds great. But maybe I'm going to get greedy here. What if we compound the interest semi-annually, meaning we compound it twice per year? So we're going to do the calculation the long way first, just so you all can see this. So if I compound the interest twice per year, here's what's going to happen. After 6 months, I'm going to get half of the interest. So after 6 months, well, the interest is 100%, so I'm going to get 50%. So what's 50% of $1? 50 cents. So after 6 months, you owe me $1 plus 50 cents. But now, that's the amount of money that you owe me, right? We're saying, okay, now that's how much you owe. And so now we're going to calculate interest on that. That's the idea, is that whenever you're earning it, like, so I'm gonna be like, I'm gonna pretend like I invested $1, I'm earning interest on that dollar I invested. So after 6 months, my dollar earned 50% of the total 100% of interest it's gonna get. So now I earn 50 cents on my dollar. And now we're going to let all that $1.50 sit in the bank or sit in you owing me money and earn interest. So for the next 6 months, my $1.50 is going to earn how much interest? Well, it's going to earn what percent? The other 50%, right? We already got half, I got 50%, but I totally get 100%. So what's 50% of $1.50? 75 cents. So after the next 6 months, I get the other half of the interest. So I'm going to have my $1.50, which is what's already sitting in the bank or sitting in the you owe me money place, plus half of that, which is 75 cents, for a grand total of $2.25. So at the end of the year, you're going to owe me $2.25. Now, let's see how the formula actually does get us there. Because you don't want to do this every time, right? I don't want to do this like 4 times and be like, okay, after 3 months, I'm going to calculate 25% of the interest and get $1.25, and then take that $1.25, and after another 3 months, calculate 25% of that, and after another 3, right? That's going to be tedious. And the point is the formula negates having to do that. We can just plug it in the formula. So if I set n equal to 2, my formula is going to say that the amount you owe me after 1 year is going to be 1 plus 1/2 to the second power. And I should have left myself a little more room here. Oh well. So 1 plus 1/2 is 2 halves plus 1/2, which is 3 halves. And if I square that, nice thing about squaring a fraction is you just square each part. So 3 squared is 9, 2 squared is 4. We're going to get 9/4. And if you change that to a decimal, 9 divided by 4 is 2 1/4, or 2.25. So it's exactly what we thought it should be. Notably, or maybe not, the increasing the number of times we compound it ended up increasing the amount of money that was earned over the year, or the amount of money you earned over the year. All right, so if we do it quarterly, the same sort of thing is going to happen. We're going to end up accruing more interest over that year period. So we're not going to do the same calculation. We're just going to plug it in the formula. So now we're going to say that if n equals 4, well, we're going to owe $1 plus 1/4 to the 4th power. This is where things start to get a little bit ugly. 1 plus 1/4 is 5/4. 5/4 to the 4th. We could still calculate this without too much terribleness. 5 to the 4th is 625. 4 to the 4th is 256. It's kind of funny how they all have the same digits there. Just a total coincidence. And if you do that division, you get approximately 2.44, or $2.44. All right, making money. Do you think I can earn $3? Can I triple my money? Probably not. We'll see though. So the question is though, is there going to be some sort of, I guess, upper limit as to how much money I can get if I keep compounding the interest more and more frequently? Well, let's look at a couple more examples and then we'll kind of come to a conclusion here. So if I set n equal to 52, if I compound it weekly, my amount of money after 1 year is going to be 1 plus 1 over 52 raised to the 52nd power. And this is definitely just to throw it in the calculator. So just to show you all, right, here's how I would do this on the calculator, on my not favorite phone calculator here. Ooh, it's big. All right. So I would do 1 plus 1 divided by 52. I would get something terrible like that. And then I would raise that to the 52nd power. X to the Y, 52. And we get 2.6925, etc. So about $2.69. And if you do it daily, that's going to be 1 plus 1 over 365 to the 365th power. And that's approximately $2.71 and 45 hundredths of a cent. Okay, so here's the thing I want you all to know about this, because this is what's really the point. We're very close to kind of the upper limit as to how much money I can get back. And the amount of money I can actually get back if I like keep compounding more and more, like if I compounded it every minute, it would be a little bit more. In fact, let's do the calculation here. It's kind of gross, but let's do it anyway. So if I compound it every minute, I'm going to be 1 plus 1 divided by 525,600. Whoops. I hate it when I do that. Is there a way to go back? Probably, but I don't know what it is. I'll just do it again. 1 plus 1 divided by 525,000. Right? This is why I don't recommend the phone calculator. That seems wrong. Doesn't that seem wrong? I should start over. Let's start over again. Right, that's the problem with the phone calculator. Let's make sure. So it should be a number that's very close to 1, right? Like super close to 1. Let's see. Okay, that looks much better. And we're going to raise that to the 525,600 power. And we're going to get not a lot more, right? Compounding every minute only increased the amount of money I got from $2.71 and 45 hundredths of a cent to $2.71 and 82 hundredths of a cent. So like barely any more money. I don't want to put all that effort for it. So here's what's happening. And this is kind of the important thing you all want to know. As n keeps increasing, this amount, the amount of money we're going to get, which is 1 plus 1 over n to the nth power, gets closer and closer to a very special number. That number is the natural base. E is approximately 2.7. And that is really all you need to know, I think, as far as how, like what number E is about. But really, the more important piece of information about E is it's actually what happens when you take this expression and let n get very, very, very large. Or in the words of limits, which you'll definitely learn about when you take calculus, if you haven't already seen them, if you took the limit of this expression as n goes to infinity, then this value approaches E. So again, we're not going to talk really about limits in this class, but it's not terrible to talk about the language or something you'll be seeing in the next math class you take. So that's kind of the idea here, is that this expression gets closer and closer to E. So E is a great number. It's super important. It comes all the time. It's definitely the base I prefer when I talk about a natural log or a logarithm, I should say. But that's where that's coming from. So why do we care about this in this context? Well, because what we're going to do is we're going to say, instead of compounding the interest daily or minutely or every second or every millisecond or whatever, we're going to say we're going to compound the interest continuously, meaning every possible moment that exists for compounding the interest. So that is actually the idea of letting the number of times we compound interest per year get infinitely large. What we're saying is we're just compounding it as many times as possible during the year. So here's what we've got. For continuously compounding interest, the formula is PERT. PE to the R. I always thought like PERT is the shampoo, conditioner, right? In one, a thing, maybe, I don't know, probably not. There used to be a shampoo and conditioner in one called PERT. And I was always like, oh, when I learned the formula, oh, PERT. Anyway, this is the formula for continuously compounding interest. And here's why it's the formula. Because what we're doing is we're taking our old formula, A equal to P times 1 plus R over N to the NT power. And we're thinking of it in the following way. We're thinking of it as, now here's where things are going to get a little dicey. P times, I want 2 brackets there, times 1 plus R over N to the N over R to the RT power. Now I want to point out, those are the same. If you multiply those powers, you multiply N over R times T, what cancels? The R's. And so you're left with what? N times T, which is what we have over here. So really these are the same. But the reason I'm writing this part this way is because this exactly looks like, or looks very similar to, something like one plus 1 over N to the nth power. Yeah, there's an R there that makes it a little bit different, but it doesn't really change. So that's exactly why we kind of talked about that, because this part here, oh, this is going to get closer and closer to the number E as N gets very, very large. So this is going to get closer to, or I should say, this goes to, is the words we use, P E to the RT as N goes to infinity. And maybe I'm saying more than is really necessary, because honestly, if someone said continuously compounding interest, you don't need to know all this background. I think you should know it, like it's worth seeing. It is good to know where things are coming from. But at the end of the day, if someone's asking about continuous compounding interest, all you really need to know is, oh, PE to the RT. So if I say I'm compounding monthly, I'm going to use the compound interest formula, 1 plus P times 1 plus R over N to power. If I'm compounding continuously, I have to use this version of the interest formula instead. And they are distinctly different from each other. So let's look at this next question. Suppose we invested $100 into a savings account that compounds continuously. After 20 years, we have $500. What was the interest rate? Well, again, this is just a identify all the pieces and then plug it into the formula and try to solve for the thing they're asking for. So we can see here that our principal is $100. Our interest rate is unknown. The amount of time is 20 years. And the amount we're going to have at the end of the day is $500. Or I should say at the end of the 20 years, not the end of the day. Notably, we didn't have to identify N because N doesn't show up in this formula. If we're talking about the continuous compound interest formula, it's this, and there is no N in there. So we're just going to throw all this into our formula and say, okay, 500 equals 100 E to the R times T. So 500 equals 100 times E to the R times 20. And just like the other problem where we had to solve for something in the exponent, we're going to do the same kind of thing. This process is going to get very, very repetitive, where if we're solving for something up here, we're going to divide both sides by this coefficient and then take a logarithm of both sides and then solve. So I'm going to divide both sides by 100. And you don't have to, but if I have R times 20, I prefer to write the constant number first. So I'm going to write 20 times R. Totally not necessary, but just seems nicer. 500 divided by 100 is a 5. 100 divided by 100 is 1, so I get 1 times E to the 20R. Now here is definitely where we should use the natural log. Right? There's no good reason to use anything else. So I'm going to take the natural log of both sides. I should say you can either take the natural log of both sides, or you can see it as rewriting it as a logarithmic equation. So actually, let's see it both ways. If I rewrite it as a logarithmic equation, okay, what's my base? What's my base? E. Log base E of 5 should equal the exponent. That's one way you can do it, just by rewriting it. Or if you prefer, you can say, I'm just to take the natural log with it. So really, I should say this is the natural log of 5 equals 20R. Or if you prefer, you can take the natural log of both sides, say the natural log of 5 equals the natural log of e to the 20R. And then the power comes down. So the natural log of 5 equals 20R times the natural log of e. But then the natural log of e is equal to 1. So really, we are just getting the same equations over here. Either way of getting there is fine. I will tell you, as we move forward, it becomes very, very common practice to take the natural log of both sides. It just kind of feels easier than having to think about rewriting it as a logarithmic equation. But it's really the same sort of work either way. So now we're almost done. We're just going to solve for r. We're going to get r equal to the natural log of 5 divided by 20. And then we should use a calculator to get the approximation. I believe, I actually remember what the natural log of 5 is approximately equal to, because I looked at the homework this time so many times. I think this is approximately 1.61 divided by 20. And that number seems familiar, I think. 0.61 is natural log of 5. And that's very close to 0.08, which is 8% as our interest rate. So that is the interest rate we would have had to have been earning for this other stuff to have happened, to be able to have invested $100 and ended up with $500 after 20 years compounding continuously. Questions about anything I've done? Okay, a couple more examples. So really at this point, the process just kind of becomes the same thing over and over again. You look at the equation, we identify the pieces we know, we solve for the piece they're asking us to solve for. So let's look at the next question. If I can move the paper here. Okay. Your goal is to have $2,000 in 4 years. Okay. The rate of interest is 10% compounded monthly. How much should you invest now? So what are they asking us to find? The amount, the principal, the interest rate, the time, the principal, the amount we're investing now, the principal. So we want to find the principal, which means we should know every other piece, right? If they're asking us to find a thing, we kind of have to know all the other things to be able to find it. So we know that the goal is to have $2,000 in 4 years. So the amount we want to have after the 4 years is $2,000. The time is going to be 4 years. The interest rate is 10%, which as a decimal is 0.10. You don't really need that 0 after the 1, but it's fairly typical to write it when you're talking about percentages. And the number of times we're compounding per year is how many? 12, right? Because we're doing it monthly. So there are 12 months in a year, so we're going to compound it 12 times per year. All right, let's toss it into the formula. So here's our formula again. A equals P times 1 plus R over N to the NT power. And then I'm going to say, okay, I've got 2,000 equal to P times 1 plus R, which is 0.10 over N, which is 12, to 12 times 4. So I've definitely seen people do questions like this in home report, and for some reason it becomes very kind of, there's like a mental block as far as how to solve for P. Let's do one thing first, but then we're going to make it fairly straightforward. So 2,000 is going to equal P times, I wouldn't normally divide this, but I'm going to here. So 0.10 divided by 12 is 0.008333 forever. This is 1.00833 threes go on forever. So we write a little horizontal line over a 3 to indicate. So this is actually equal, right? Because it's literally the same number. And then 12 times 4 is 48. Now, I don't need to take a logarithm here. There's no variable I'm trying to solve for that's in an exponent. I'm trying to isolate p. So I'm going to divide by the thing it's multiplied by. So I'm going to say that 2,000 divided by this gross number here, 1.00833 forever, to the 48th power is equal to p. I really don't want to write times this divided by this. I guess I could. Not the worst thing to have to do in the world. All right, let me ask you all kind of an easy question here. What is 1.008333 to the 48th power divided by 1.008333 to the 48th power? 1. That's why we did it. Right, so these divide out to leave a 1 behind. So now I'm left with p equal to 2,000 divided by 1.0083333 to the 48th power, which is approximately. So let me ask you, before we write down what this is using a calculator, do we expect this number to be larger than 2,000 or smaller than 2,000? Smaller, right? Because you're wanting the money to grow to $2,000. So if we do the division here and we get something bigger than 2,000, we should definitely check our work. We're not going to, but just kind of get to think about the number sense as far as like what kind of answer should we be expecting. Here, if we do this division, we get approximately $1,342.89. Okay. Let's look at the last one. Similar, but a little different. Now we're being told the amount we're starting with. So again, although I haven't always done it, I do like to try and write down things as I read them. So our principal is $1,000. We want to end up with $2,000 after some amount of time. The amount of time is also 4 years. So very similar to the previous problem. What interest rate now? So they're asking for the interest rate. Do we need if we're compounding continuously? So that's kind of all the information. The only other piece of information we need to know is the compounding continuously formula, which is P e to the RT. So, whoops, not PERT like that. That's terrible. P e to the RT. There we go. So that should be what our amount is equal to after however long. So let's throw it all in there. Let's see. So our amount is $2,000 and should equal our P times E to the R, which we don't know, times T. What do we have to do first if we're trying to solve for R? Right, we always need this coefficient to go away. So divide both sides by 1,000. 2,000 divided by 1,000 is 2. 1,000 divided by 1,000 is 1. I don't really need to write the 1 there, but I did because I did. So rewriting this, we've got 2 equal to e to the 4r. You can write r4, but usually people write 4r. It's just a better way of doing it. I don't know why it's better. Like, there's really no good reason. It just feels so wrong to write r times 4. I can't even tell you how wrong it feels. Okay, so then we're going to do what? Yeah, we're going to do the natural log, or any log, but really the natural log here, because we're trying to solve for a variable that is in the power. When that variable is in the power, you kind of have to use a natural log. I'm just going to take the natural log of both sides. The natural log of 2 equals the natural log of e to the 4r. But that allows us to use the power rule for logarithms. It says if you have the natural log of something to some stuff, that stuff gets to come down in front. So now we're going to have natural log of 2 equal to 4 times r times the natural log of e. But what's the natural log of e? 1. That's definitely a thing you want to take home with you, right? It's important to know natural log of e is 1. So this is just equal to 1. So then we're left with 4r equal to natural log of 2. If we divide both sides by 4, we get r equal to the natural log of 2 divided by 4. And that's going to be approximately, the natural log of 2 is about 0.69. divided by 4, and that's going to be approximately 0.173. So what's the interest rate that we're talking about here? Right, we move the decimal over twice and say, oh, it's going to be 17.3%. So our interest rate is about 17.3%.